Hello and welcome to the first session of the Gas Conference at ENIC 2020, where we'll be looking at the energy system transition, building the safety case. I'm Richard Hines-Cooper, Head of Innovation at Northern Gas Networks, and I'll be your host for the session. To start out, we'll be hearing from Eva Henning, the Head of Department Policy Issues at TUGA in Germany, who will be sharing a European perspective on the trialling and scaling up of hydrogen. We'll then be joined by Dr. Mark Taylor, the Deputy Director for Energy Innovation at BASE, for our hydrogen keynote. This will be followed by presentations covering the UK's largest hydrogen safety trials from my colleagues at Northern Gas Networks, National Grid Gas Transmission, SGN and Cadent. We'd like to invite you in the audience to ask questions using the text chat function to the bar to the right of your screens, and our speakers will be able to respond to you live throughout the session. And to get the best experience, we recommend that you close all other applications on your computer and check that nobody else is hogging your broadband connection.
Hello, my name is Eva Hennig. I work for the German company of TUGA, and I'm very excited to be part of your interesting conference. Thank you very much for the invitation. TUGA is the largest group in Germany with nearly 100 companies, and it's an alliance of municipal utilities serving regions and cities. They all do gas, electricity, district heating, and water. We have lots of interest in hydrogen. It's very interesting how exciting the developments are in the regions and in the cities. And we have many projects coming up from local production with electrolyzers, but also the pyrolysis. And we concentrate on the local distribution and demand. But let me tell you first something about the European Hydrogen Strategy, which came out in July. It's the first comprehensive idea for a hydrogen economy with ambitious production targets. They want to build 6 gigawatts and integrate this hydrogen until 2024 and 40 gigawatts until 2030. It is focusing on renewable hydrogen, but other forms of decarbonized gases are also seen as a necessity to speed up the decarbonization of the system. The strategy foresees 3 phases. Phase 1 is the construction of large electrolyzers close to demand centers, concentration on utilization in industry and mobility, and the planning of the EU TSO backbone, and the installation of carbon capture for existing hydrogen production. Phase 2 sees the conversion of steel production to hydrogen, the use of hydrogen as a balancing tool for the electricity system, and the creation of the regional hydrogen valleys, which is us, with decentralized production and demand in various sectors, including buildings, and the start of repurposing of the TSO gas grid and underground storages. Phase 3, which starts after 2030, is a large-scale deployment of green hydrogen, the massive increase of renewable electricity production, and the utilization of hydrogen in the various sectors. To bring all this in life, and that's a lot of organization of the different work streams, the Clean Hydrogen Alliance was founded to create a project pipeline, so a concrete pipeline in the areas of production, transport, distribution, and applications. At the first Hydrogen Forum on November 26, the work was kick-started. Coordination is key if the hydrogen shall flow from production to the end user. Blending of hydrogen to gas grids is seen as a chance to ramp up production, but it is considered as complex and not the best solution. Pure hydrogen is giving a higher value for the system, and the decarbonization of the heating sector is still promoted with electricity and district heating. What does this mean for us? We have 1,400 European gas DSOs, and we work very closely together in many parallel work streams. Most important is project, and I love what's happening in the UK because you have so many projects happening and we always look at you. We have many member states where the large amount of industrial consumers and the CHP plants are connected to the DSOs, which is often forgotten. So the TSO backbone will be key to build an integrated EU market across the borders, but the conversion will require time. Gas DSOs are the only ones able to bring renewable and decarbonized gases to end consumers long before the backbone is finished. To include the hydrogen into the existing market design will speed up the market uptake. If you don't have a regulation, the hydrogen will end up in a very small market with few customers and producers connected only to the TSOs, because if they are connected to the DSO, you need to have the regulation. Competition and liquidity needs a broad range of actors. This is what we know from the past. Guarantees of origin are needed to facilitate the trading of renewable and decarbonized gases in pure form or in blends. They offer customers the possibility to decarbonize their heating system independent of what is really flowing through the grids. the extension of the gas grid should be considered as sustainable in the taxonomy. So when you look at this, if you want to create the market, you have the legislation on the one side, which in the case of Europe is depending on the Green Deal, but you also have the organization on the other side. And when you think about the organization, as I mentioned before, we have the project pipeline of the Clean Hydrogen Alliance, but we also have the concrete projects in the countries. This is the project in Germany, where we looked at where does the gas come from and where does it go. And we are, with TÜGA, most of our companies are somewhere in the south, and that means we have to help ourselves because we cannot wait for the TSO to come. This means that we have projects. This is the one in northern Germany where you have an electrolyzer built in the refinery. We're going to inject 20% of hydrogen into a grid to serve 250 customers. But we also have a cement production which will then use the oxygen. This is the best thing that you can do. So you combine all the worlds. You have the industry. There is an underground storage, a salt cavern. But they also produce eco-fuels for the airport in Hamburg. And this is giving the benefits that you can use the infrastructure the most. But we also have another project, which is a regional DSO. It's not very large, considered the UK sizes. It only has 29,000 end consumers, but it has this very specific situation that they have 6 biomethane injection points, and they have very large industrial consumers, the biggest one that we have in the whole group. They have 3 CNG stations which are connected to the grid, and they also have 3 CHP plants, which means that already today they have to deal with all sorts of gases coming into the grid. And this was the reason why they implemented the smart SIM system, which is a smart grid system. This way we can track the gas, we can define the calorific value and also the Bobbe index at all those exit points. And we will use this when this hydrogen injection comes up here with a wind farm, that we can track the hydrogen. And what we will do then, we do a forecast to know where the hydrogen will go. And this is very important if you want to operate this kind of a system. Here you can see the simulation running with all the different kind of injections that we have, and we can always track where the gas is flowing to the end consumer, which is very important if you want to make sure that the gas is, that you always know, for example, how much hydrogen is in the grid at the specific point of the exit. This was just a very short introduction of what we are doing in TÜGA and what is happening in Europe. And again, thank you very much. If you have any questions, I'm still here. Bye-bye.
Hello everybody, my name is Gunhild Eikstad and I'm a research manager at SINTEF Energy Research, located in Trondheim in Norway. Today I will present to you a few highlights from the Elegancy Project. Elegancy is the acronym for Enabling a Low Carbon Economy via Hydrogen and CCS. And it is a project that is funded by a Highnet co-fund project called ACT, standing for Accelerate CCS Technologies. As you can see in this figure, the main focus of the Elegancy project is to develop technologies for production of hydrogen from natural gas, where the produced CO2 is captured, it's transported, injected, and stored permanently. In addition to this kind of production technologies development, there are also other aspects that are important when dealing with hydrogen and CCS value chains. And so the Elegancy project has also developed tools, for instance, for business case development and also for infrastructure optimization. In addition, the Elegancy project has dealt with social acceptance issues as well as environmental aspects. Further, the Elegancy project has included 5 case studies where the design of these studies are such that they have been set up to incorporate and to adapt the knowledge that has been generated within the Elegancy project to national conditions in the assessment of national business cases for hydrogen and CCS value chains. And so today I would like to focus on the case studies and the case studies results. And on this slide, you can see the main topics that has been included within these case studies, where there is one case study per participating country. So as a key part of the work with the case studies has been to identify the potential role for hydrogen in these countries or in regions of these countries. The next issue has been to work on the planning of the infrastructure development. And to this end, the optimization tool for infrastructure development has been applied in several of the case studies. The business case development tool has been used for business case development, and environmental aspects has been investigated through life cycle analysis, and social aspects has as well been investigated by investigating the societal support for hydrogen and CCS value chains. Today, I would like to mainly present to you 4 observations of what we have found significant from the case studies. First observation is that the industry sector is key in realizing a hydrogen sector that is at a sufficient scale to achieve the reduced costs for the hydrogen economy. The second observation is that business cases for hydrogen and CCS value chains must be defined and evaluated in this context of reaching net zero by 2050. And specifically in the UK case studies, it was found that a delivery body or organization is required, and this organization must have a clear mandate to coordinate the UK system-wide business case for all regions and all sectors. And this is key in steering the country towards a net zero economy by 2050. Third observation is that it has been found for several of the cases that if you are to develop cost-effective infrastructure, this relies on the availability of sufficient storage facilities for both hydrogen and as well CO2. And hence, these kind of aspects are key when assessing the possibilities for developing a hydrogen economy and also for developing hydrogen and CCS value chains. And the last observation that I would like to focus on today is that although we in the case studies have been working on establishing national case studies and national business cases for hydrogen and CCS value chains, we see that the transnational collaboration is also essential in establishing the hydrogen markets nationally. So I would like to emphasize that it is important to take into considerations the national conditions. Which sectors are the most important? What are the main restrictions? What are the main opportunities for realizing a hydrogen and CCS value chain? It is to a large degree dependent upon the national conditions. But we also need a very clear transnational collaboration, both for CO2 transport and as well for transnational exchange of hydrogen as well. And in the Elegancy case studies, the transnational collaboration has been seen, for instance, in the relation between Germany and the Netherlands, where the CO2 produced and captured in Germany has been assessed to be transported to the Netherlands for permanent storage. In the same way, hydrogen produced in Norway has been evaluated in terms of at which cost and at which quantities it could be exported to Germany. Further, in Switzerland, it has also been assessed the potential for a domestic CO2 storage, and it is seen that in the short term, it is very important for Switzerland to be able to export its CO2 to existing or emerging CO2 storage facilities, such as the Northern Light projects in Norway.
My name is Mark Taylor and I'm Deputy Director for Energy Innovation at BASE. And I'm delighted to be here to discuss the role of innovation in developing hydrogen as a solution for delivering net zero by 2050. Achieving net zero greenhouse gas emissions in the UK by 2050 is now set in UK law. And in this slide, I show you our progress to date. And as you can see, this has been considerable. Since 1990, we have significantly reduced our emissions, particularly in the power sector, moving away from coal towards natural gas and renewables. We've also made significant progress in our waste management, mainly by capping methane emissions. However, as we sit here in 2020, in order to achieve 2050 net zero, we appreciate that we have to tackle the much more difficult sectors, including domestic heat, industry, and transport. And our analysis shows that hydrogen is a key vector for achieving progress in all of these areas. In this slide, I show you predictions made by a number of parties about the amount of hydrogen we will need in 2050. As you can see, these volumes of hydrogen are considerably larger than our current approximately 10 terawatt hours of hydrogen being used in the UK. So we will have to increase our hydrogen production by at least 1 order of magnitude and even towards 2 orders of magnitude by 2050 in order to realize a net zero achievement. I'm now going to discuss in more detail what we've been doing in BASE using our energy innovation portfolio to develop solutions in this area. Now I present a schematic of how a 2050 hydrogen economy could look. And as you can see, it's quite complicated, including capacity to develop blue hydrogen, so that's making hydrogen from methane and capturing and storing the carbon dioxide that is emitted as a result, and also the capacity to take green hydrogen, particularly from renewables. We also need to incorporate storage, particularly for interseasonal storage, and as well, you can see we're able to show that we're able to supply all 3 vectors I discussed in the last slide, including transport, domestic heat, and industry. And I will now move on to show you how we intend to tackle this via innovation. So we started our innovation competitions with a focus on hydrogen supply. Obviously, for a hydrogen economy, you need hydrogen. But we wanted to ensure that any hydrogen we were making was going to be compatible with net zero. And that means replacing the current technique of steam methane reformation with either blue hydrogen, which is steam methane reformation with carbon capture, or green hydrogen. And indeed, we are trying to support the development of both technologies. In this slide, you can see we received an overwhelming response to our original £20 million competition and ended up allocating £33 million for this competition. This includes a development of advanced thermal reformers, which have very high carbon capture rates, with a view to deployment in UK industrial clusters by the mid-2020s. We are also supporting the development of green hydrogen technology using offshore renewables, including a project generating hydrogen using floating offshore wind. Now I'd like to present a case study of one of our green hydrogen supply winners. This is a consortium of Ørsted, ConocoPhillips, and ITM. And what they're looking to do is to take renewable electricity from offshore wind, produce large volumes of hydrogen using a large-scale electrolyzer, and use that hydrogen in the refinery process to drive down CO2 emissions. And on the graph on the left, you can see ITM's own analysis of the impact of the BASE innovation funding. And their graph clearly shows that our innovation funding intervening at this stage greatly enhances their chances of delivering large-scale electrolyzers by 2030s. And this is exactly what we want to achieve. And as you can see, it includes a FEED study for a 100 megawatt electrolyzer That's an order of magnitude larger than the largest current electrolyzers. This is exactly the scale we need to meet the volumes of hydrogen production I talked about earlier in this talk. A particularly exciting component of this project is that, as well as developing the technology for the electrolyzer itself, we are supporting the development of the manufacturing equipment to enable large-scale production of these electrolyzer stacks to happen. And indeed, this is leading to the development of the largest PEM electrolyzer factory in the world, in Sheffield, by ITM. You will shortly hear from a number of the other speakers about the innovation that's taken place using Ofgem supported programs, NIA and NIC. And they will tell you about how we are developing solutions to decarbonize the national grid and the distribution grid, ready for the hydrogen transition. But I'm now going to talk about one of our innovation programs, industrial fuel switching, which tackles the decarbonization of industry. And in beginning this program, we first did a comprehensive survey of the industrial sectors in the UK and identified decarbonization routes for all of the industrial processes that are currently taking place in the UK. And what we found was that hydrogen was a key vector for a large number of these processes. However, we met one challenge, that many of these solutions are at quite low TRL levels, so typically between TRL 4 and 7, and nowhere near the TRL 9 level required for any industry to convert fuel with confidence. And what we want to do with our program is develop programs that would enable us to demonstrate and start to develop these solutions and move them up the TRL levels, ready for deployment in a hydrogen economy. I would now like to showcase the Highnet Project, which has benefited from two of our innovation programs, the Hydrogen Supply Competition and the Industrial Fuel Switching Competition. In this program, they will be developing a low-carbon hydrogen production facility using Johnson Matthey's Advanced Thermal Reformer. This will be installed at the SR refinery site, and we will also look at the usage of hydrogen following this project. This includes a CHP at the refinery site, and also looking at the use of hydrogen for direct firing in the manufacture of glass at NSG Pilkington, and the use of hydrogen boilers at Port Sunlight Unilever site. And this is a demonstration of both how a hydrogen economy might work, and indeed there is plans by using blending as a means to boost hydrogen consumption to be able to convert the entire Northwest to a hydrogen economy. We're delighted to be supporting this work. I'm now going to discuss one of the biggest challenges we face, which is the decarbonisation of domestic heat. 85% of UK homes are on the gas grid at the moment, so they are heated by methane. And methane, when it's burned, produces water vapour and carbon dioxide. And we would like to explore using hydrogen in place of methane. In order to do that, there are a number of fundamental things we need to do because the physical properties of hydrogen are very different from methane. The way it burns, the way it behaves as a gas, the way it diffuses needs to be understood, and we need to develop appliances that can effectively use hydrogen safely in the home. And to do that, we have developed domestic appliances using the Hy4Heat program. We've developed commercial appliances. We have investigated and evaluated solutions for industry, some of which I've already shown you. We have also developed hydrogen meters, because obviously we need to be able to measure, just as we do today, the amount of gas being consumed by the consumer. We have also developed a number of key standards, including pass standards for hydrogen appliances, and we are currently preparing the ground for pass standards for the installation of hydrogen appliances. And we have also developed standards for gas, for hydrogen gas, and definitions that can be used in any national rollout. We are doing this work to prepare the ground for community trials where we can deploy hydrogen in a community, demonstrate its effectiveness for the consumer and its safety for the consumer. Here is some more detail of the appliances we developed under the Hy4Heat programme. Of particular interest is the concept of hydrogen ready, which we've deployed on our hydrogen boilers. So rather than producing hydrogen boilers, we produce boilers that can run on both methane and hydrogen. And what it involves is you could buy a hydrogen ready boiler on the market, hopefully by 2025, and burn it with methane and burn methane with it. But if your area was to convert to hydrogen, for example, in 2028 or 2030 or even later, you could deploy a kit that would convert that boiler into a hydrogen boiler. And this would be at minimal charge on top. So this would allow us to start a rollout of boilers that are ready for a hydrogen transition before we have made a final decision about the hydrogen transition. We've also developed a number of appliances. I've shown you here a hydrogen fire and a hydrogen oven. And I hope you'll agree with me that the flame looks very nice indeed. And I think this has set an important step forward to give the government confidence to proceed with a hydrogen rollout. And you can see from the Prime Minister's recent 10-point plan for a green economy, we can set out ambitions to have a hydrogen town by 2030. Of course, there's a lot of work to be done before that, but Hy4Heat has already had a positive effect on government policy and allowed it to send positive signals like this. This slide shows how comprehensive the Hy4Heat work has been done in developing our knowledge and understanding of hydrogen. This includes the development of a hydrogen knowledge centre, which is to be hosted by iGEM, will allow us to collate all the relevant information that anybody can use in the UK to help us move forward towards a hydrogen transition. We've also dealt with standards of purity, odorant, and colorant, and developed much more understanding of what needs to be done. The most important component of which is the development of a safety case, which we have currently submitted to the HSE. And what we're looking there is to persuade the HSE that we understand hydrogen well enough to be able to proceed with small-scale trials. And then over the coming years, we will seek to develop our understanding further to enable us to move towards larger-scale trials and indeed a hydrogen town by 2030. As well as establishing a robust safety case for the use of hydrogen in the home, it is very important that we can demonstrate to consumers the capabilities of hydrogen and the behaviour of hydrogen in the home. And as part of that, we have developed a number of demonstration facilities. One is a mobile facility, which we'll use to showcase all of the Hy4Heat programme work at COP26 next November. But we are also looking to expose the consumer to hydrogen. And one way we can do this is with our current Hy4House call, which is looking at 1 or 2 hydrogen homes that can be visited by members of the public, but also by politicians and local politicians and other stakeholders that we may want to engage preparing the ground for a trial. Now we need to think about next steps. And in fact, the next steps are really building on this foundation and continuing to develop technology, move it up the TRL levels and prove it, particularly for industry. So we need to develop appliances in the industrial sector that industry can be confident in will deliver when they switch their production lines to hydrogen. We also need to start moving towards deployment. You've recently seen from the Prime Minister's 10-point plan, the government will start to invest significantly in low-carbon hydrogen production facilities. And it's really important we do that because we need the hydrogen production capability in order to get net zero, but we also need that volume of hydrogen to do the testing that we need for industry and to do the trials that we need to do to prepare the ground for deploying hydrogen for domestic heat. We also need to continue to develop on the work we've done on Hy4Heat. That includes developing further standards, skills training, and further refining the safety case, particularly with a view to more complicated properties than the 2 up, 2 down that we've looked at so far. And of course, because of the progress we've made on innovation, it's critical now to consider further innovation in the context of policy development. And you can see in this slide, I list a number of the initiatives that will come to fruition in the coming weeks and coming months. And these will be critical for enabling the rollout of hydrogen and also providing an outlet for the hydrogen technology I've talked about that we are developing. So these include the hydrogen strategy, which will come out next spring, which will include tackling the development of hydrogen business models so that we can understand how hydrogen can function in the market and compete with high carbon fuels. Also, in the longer term, we have the opportunity of COP26 to showcase what the UK is capable of. And we're also developing a number of strategic papers, including the Energy White Paper, which is due quite soon, and then also industrial decarbonisation strategy. And all of these provide the ideal landscape for us to turn the innovation that I've just shown to you into deployment, and more importantly, into solutions that will deliver net zero. Thank you very much.
Hi, I'm Tim Harwood, H21 Project Director, and I'm going to spend the next few minutes giving you an overview of the H21 suite of projects. So what is H21? Well, basically H21 is a suite of pioneering gas industry projects that are sponsored by Ofgem. They're led by Northern Gas Networks, but we also have a number of different partners, as you can see at the bottom of the screen. It's a great collaborative piece of work, and it started in 2018 and potentially could run through till 2024-2025. The purpose of H21, in a nutshell, is to focus on demonstrating that the existing UK gas distribution grids can be repurposed to carry 100% hydrogen in a very, very safe way with minimum disruption to customers. So what have we done so far? H21 is split into 2 phases at the moment, with the potential for a 3rd phase, which I'll come on to speak to you about at the end of the presentation. So phase 1A is almost complete, and it involved building a new test site at the Health and Safety Executive Science Division labs in Buxton. Assets were removed from the distribution network, taken to Buxton and tested for leakage. They were tested to see if they leaked any differently with natural gas as they do with hydrogen. All sorts of different assets were taken out of the ground, some of them up to 100 years old, of all different types, metallic, polyethylene, steel, also valves and fittings and pressure regulation equipment. So the whole remit of things that you'd expect to find on a gas distribution network. The testing was really successful, and without preempting too much the outcomes, because the phase 1 report is going to be released in January 2021, so I don't want to preempt too much the findings, but the overall view of the team is that the leakage test went really well, and there wasn't really any difference between hydrogen leakage and natural gas leakage, in so much that if it didn't leak with natural gas, then it didn't leak with hydrogen. Phase 1B was taking place at DMVGL's site at Spade Adam in Cumbria. And what they did there is test the consequence of gas escaping out of pipes and out of the network and tracking across ground and getting into houses. What would that do from a risk basis? How would that migrate across different types of ground, made up ground, grass, unmade, tarmac flags, those types of things? How would the ignition potential and explosive limits be different? How would that compare to natural gas? And at the end of it, we need to do a quantitative risk assessment to look at whether the risk to hydrogen is any greater or lesser than the risk to natural gas. And that's what we're doing at the moment. The phase 1A and 1B are more or less complete, and we're now just writing up the report, ready to do some webinars in the early part of 2021. We'll be able to provide more details of how you can join the webinars and how you can receive the report in due course. Another important part of the H21 trial is the social sciences. We feel this is just as important as the scientific research, in that we must have social acceptance of hydrogen in order to be able to push forward the programme of widespread conversion of networks. The great news is we worked with a fantastic university in Leeds called Leeds Beckett University. They're really good at doing the social sciences work, and the results are really good for us and really positive. The public felt that safety wasn't a major concern. Obviously, cost and disruption are the two main barriers, but it was felt that if we took a big step towards decarbonisation by converting the networks to hydrogen, then they would be prepared to pay a small premium for that. They're able to digest quite technical information and return it and explain it, but what they don't like is acronyms. They don't like difficult terms like decarbonisation and some of the other things that you can see there, like carbon capture and steam methane reforming. They want to be told the facts, and they want to be brought along with the journey, but they'd like it to be done in plain English. Keywords and phrases are important, and some of the further research that we've done in phase 2 of the social sciences shows that how you explain to customers via letters and social media, how you change keywords are very important in getting them to understand and sign on to what we're trying to do. So alongside the safety related stuff, it's very, very important that the social sciences are also taken account of, and it's every bit as important as the safety related things that we're doing at the moment. So H21 Phase 2A and 2B is really exciting that we started doing these projects at the beginning part of 2020. We've had a slight delay and interruption due to COVID, as everyone else has with the projects that have taken part this year. But we're not deterred, and we are still ploughing on, and both of these projects are now up and running, and we'll be able to do experiments during 2021 with the view to finishing these projects off at the end of 2021 and publishing the final report at the start of 2022. So yeah, really excited that these two projects have now got off the ground. So Phase 2A is a microgrid that we're building on the existing DMVGL site at Spade Adam in Cumbria. If you look at the left-hand photograph near the top right-hand corner, you'll just see the outline of the high street, which is the houses that we showed you in the previous slide. Inside there, we've got a number of hydrogen-ready appliances, and what we want to build to the left-hand side of there is a copy in a small scale of a gas distribution grid. So we're busy doing all the groundworks at the moment and putting all the pipes in. The pipes are all different sizes, different types of pipes. So you've got polyethylene, you've got cast iron, steel. We've also got pressure reduction equipment and valves and all the other peripheral stuff that you get on a gas distribution network. So the idea is that we're going to fill that network with 100% hydrogen, and we're going to create a flow around the network as you would in a normal distribution network. We're then going to go out and do operations and maintenance as you normally would. We're going to attend to gas escapes, we're going to relay services, we're going to extend the network, put new connections in, cut pieces out and do replacement. Basically all the tasks that you'd normally expect a gas distribution network to undertake in a real life situation. And from that we'll get lots of learning on being able to use new tools, new equipment and techniques, put into place changes to procedures from what we use in existing natural gas, and just to see and practice the look and feel of working on a gas distribution grid, but in a safe environment. The great additional news here is, if you can imagine to the left-hand side of the photograph on the left, there's going to be National Grid building their own rig. They've put a bid in to Ofgem for something called Future Grid, which is a transmission grid that will attach to our distribution grid. You'll then have the whole end-to-end process. We'll be able to put hydrogen into the transmission system It will then flow around and go into the distribution system, which will then flow into the houses and then through the appliances. So you basically got a copy in a microcosm of a small distribution and transmission network in the UK, which is going to be fantastic news. So fingers crossed that National Grid will get their funding and will be able to build the extension to the grid. The unoccupied trial site as part of Phase 2B is in Redcar near Middlesbrough. And we've been working with Redcar Council, and they've kindly given us a couple of streets of demolished houses. So as you can see in the photograph there, this is a normal street scene that you would find in a town, but the grassed verges are where the houses used to be. So the houses have been demolished, but all the infrastructure still remains in place. All the buried underground services, not just the gas network, but there's telecoms, water, electricity, drains and sewers, and all the normal things that you'd find. And again, what we're going to do is then have an opportunity to disconnect the gas from the existing gas distribution network and fill it with 100% hydrogen. We're then going to go out in a more realistic street scene scenario and practice operations and maintenance, repairs, gas escapes, extensions to the network, as I've said, in a more realistic setting. So this is a fantastic opportunity to us to do a stepping stone between the scientific research on sort of closed, secure sites and taking it out into the public domain. So a brilliant opportunity for us, and we are going to be getting going in the sort of first quarter to second quarter of 2021 out there in Redcar, and we're really looking forward to doing that and interacting with the public as well as we go through and do the trials in a safe manner. At the end of doing both of these trials, when we publish our final report on the H21 Phase 1 and Phase 2, we hope to be able to demonstrate that we can operate networks just as safely, if not safer, than we do now with natural gas. We need to get a sign-on from the Health and Safety Executive that they're happy that we've met all the requirements to be able to do live trials. And then we're actually going to move on to do 100% live trials out there in the community. So I'd like to spend a couple of minutes talking about the potential next phases of H21, Phase 3 and beyond. We've got a funding bid in, and we're talking to BEIS at the moment about Phase 3, which would be a continuation of the work from Phase 1 and Phase 2 and basically would finish the programme off. So we'll have gone from scientific research through to trials on secure networks and unoccupied trials. And now we need to finish off the programme by doing trials actually out there in the community of live 100% hydrogen in people's homes. So we've put forward a proposal to do a trial starting off with 3A, which is 50 houses, and then Phase 3B is a further 620 houses. The timings for those are Phase 3A, if everything goes well with Phase 1 and Phase 2, and we get the sign-off from our regulators, we could be potentially doing live trials in houses by the midpoint of 2022, and then approximately 12 months later, expanding the trial out to a further 620 homes for another year. So you're talking about mid-2024 getting up to 2025 when, you know, we could have finished our programme off and demonstrated that we can run and manage safely and effectively 100% hydrogen networks. And then we should be getting ready for conversion after that. It's a case of a government policy decision coming along and the stimulation of production, so there's plenty of hydrogen freely available to start going around and planning out to do conversions. We're really pleased in Northern Gas Network's geographic patch that we've got places like the Teesside and the Humber region that are touted as being the start of the industrial clusters. So there'll be the decarbonisation of large process plants, power generation, steelworks, glassworks, those types of things, but also making sure there's enough hydrogen available to do homes. We've got appliance manufacturers who are now making 100% hydrogen ready boilers, and within the next 12 months there should be a whole range of new appliances coming out that have been approved. So basically we're really excited about the future. We think that we can finish off this programme of work and demonstrate beyond doubt that we can run hydrogen networks and that they will be as safe as natural gas networks. We can repurpose existing pipework and therefore cause much less disruption to the public and much less cost than there would be if we did things like all electrification or started installing heat pumps. Now, it's not to say that those things aren't valid in different scenarios and different places. We need a whole systems approach to this. There's not one silver bullet that fixes everything. But we believe one of the key components of decarbonisation of heat in homes is repurposing existing networks to run on 100% hydrogen. And we feel that the programme of work that's been put forward by H21 is progressing well. There's lots of work to do over the next couple of years to get to where we need to be, but we're very excited about being part of the hydrogen journey. So that concludes the presentation. I hope you found it informative and interesting, and I'd now like to hand back. Thank you.
Welcome everybody, my name's Tony Green and I'm the Project Director for Hydrogen at National Grid. I'll just let my colleagues introduce themselves.
My name is Lloyd Mitchell, I'm a Pipelines Engineer and Innovation Project Lead within National Grid.
I'm Tom Neal, the Innovation Delivery Manager in National Grid.
And our presentation today is looking at the work that we've been doing over the last year or so, looking at how we might transition the gas transmission network to carry hydrogen. It's our HINTS programme, as we call it. So we're going to take you through some of those projects and then look at the Future Grid project, which is our very exciting offline transmission test network that we're working towards. So just to set the scene, I'm going to look at some of the aspects of transitioning to hydrogen. As a transmission network, we sit very much in the middle here. We need hydrogen production to take place, and we need hydrogen use, hydrogen demand to start to occur before we can actually start doing our jobs. To move gas from A to B. So, as I said, we're very much in the middle here. We're very focused on ensuring the readiness of our assets, looking at can we convert the assets, do we need new build of assets, can we carry a blend of hydrogen, or do we move up to 100% of hydrogen? And then how do we actually go through that conversion? Do we go pipe by pipe, or do we do sector by sector, a more incremental type of conversion? So there's lots of details to look at here. And as we start to look to the conversion of the network, we have developed the concept here of Project Union, which is a hydrogen backbone. And the idea behind Project Union is to join the dots, for want of a simple term, between the industrial clusters. You can see the scale of the carbon emissions from the 5 industrial clusters that we've got around the UK. And by lifting a hydrogen backbone between those assets, we start to form a lot of resilience between the assets, so that they are able to operate more efficiently. They've got more system security available to them. The other aspect you'll see in here is that we've created a link down to our Project Cavendish, which we finished last year. Project Cavendish is a hydrogen production facility, and we've also connected over towards Bacton, and this is to tie in with the European hydrogen backbone. So this is in concept phase at the moment. We're working through the realities of this, looking at the feasibility and the timing of it, and it's something I'd hope to be able to talk more about in the future with you.
So first, to understand the context behind some of the projects that we've got going, it's important to understand what are the key knowledge gaps that we're trying to address through these projects. So we've got picked out the 5 principal knowledge gaps that we're looking at through these projects at the moment, and I'll just go through those in a little bit more detail. So the first of all is the first of them is materials concerns, and that's looking at things like what the materials effects on pipelines and mechanical assets. So you may have heard of hydrogen embrittlement. It's trying to understand what that means for our pipelines, whether we can still operate as we do today, or whether we need to introduce some sort of mitigations to reduce the effect that has on the pipeline steels. Also looking at things like soft parts and seals. We've heard that, for example, metal sealing valves perhaps are more suitable for hydrogen than soft sealing valves. And also looking at things like weld quality and how that affects, how that interplays with the hydrogen embrittlement to change the risk profile of our pipelines. So the second is safety concerns. So hydrogen is quite a different gas. It has different characteristics in terms of sort of building proximity distances, the heating value from flames and explosions. So we've got to rethink things like the hazardous areas around our equipment. It has a different gas classification in terms of the electrical equipment you can use around it. So we would have to evaluate all the electrical equipment across the network and understand whether that's still compatible. And we'd have to change the way we do plant operations. So things like venting, for example, hydrogen can be quite a lot louder when vented, and there's the environmental concerns there with our sort of neighbours around our above ground installations. So those are the sorts of considerations we're making around safety. We've got to understand in a bit more detail the flow characteristics. So how does the hydrogen move around the network? So interestingly, although hydrogen is more energy dense per unit mass, it's actually less energy dense per unit volume because it's so incredibly light. So it's trying to understand how we can push a bigger volume of gas around the network, but perhaps we can increase the gas velocity because there'll be less saltation, so that's sort of erosion on the internal pipe walls, and there potentially be a smaller pressure drop. So there's all these sort of interplaying characteristics we have to understand for how we move the gas around the network. And related to that, we have to understand how that would change our compressor strategy. So the turbine manufacturers are looking in great detail at their own turbine compatibility with hydrogen, but we need to then map that across our network and try and understand how that impacts our investment cycles going forward, because these large plant pieces of equipment often have a 25-year life cycle. So we've got to think about how the gas network is going to change when we're making our investments today. And then finally, network management, which sort of links back to flow characteristics. We've got to ensure that we can maintain security of supply, because that's a really important objective for us. And so how does that, so for example, we have less inherent storage within the network with hydrogen. At the moment, we have sort of a day or more of storage just within the gas that's contained in the network, but because of the decreased volumetric energy density of hydrogen, that's going to change. So how does that change the way that we manage the network? And what are the other factors we need to consider, things like deblending, or whether there's going to be distributed hydrogen coming onto the network. So to give a little bit more detail about some of these projects, I'll go through a few now. So there's the feasibility of the NTS project. So that was an initial look at the materials effects that was done with the Health and Safety Executives science team. And essentially what that looked at was the very first pass saying, can the gas networks transport hydrogen, yes or no? And so to that end, it was quite a promising result. Although there are effects from hydrogen embrittlement on our pipelines, these can be mitigated, and it's not, the network is by no means a write-off. There's a lot of things we can do. For example, small amounts of oxygen can almost completely negate the effect that hydrogen embrittlement has on our pipelines. So that's a really positive finding that we're looking at evaluating further. We can also change operational practices. So, for example, we pressure cycle the pipes at the moment. We sort of ramp up the pressure generally overnight to sort of make use of that inherent storage and then drop it down over the day. But we might change the way that we do that to, again, mitigate the effects of hydrogen embrittlement. So hazardous areas I've talked about as well in terms of electrical equipment and ATEX equipment. And there were quite a number of materials issues identified, 69 that we identified through this project, which we're evaluating at the moment. But it's all stuff that's in hand with the Future Good project that will be talked about in a bit more detail later. Looking at deblending, so I mentioned just earlier around how we might need to change the way that we operate the network. So deblending is just one example of that. You may have heard recently with the announcement that we're looking at blending hydrogen onto the network. We've got to think about where there might be customers who might not necessarily be ready for hydrogen. Is there a way that we can separate the hydrogen out for their particular facility and then transport that down the rest of the network to a customer who can accept it? And so there was a project evaluating the impact of that. and this was done in collaboration with the other gas networks, the gas distribution networks, and it was all using well understood chemical industry technology, and there's again quite a positive result in terms of it being possible, and then there's just more work to be done to understand what it might actually look like. And other projects of note would include Aberdeen Vision, so that's looking at whether we can inject hydrogen at the gas terminal at St Fergus, and then flow that down sort of north to south into the rest of the network. And that's quite an interesting project in terms of understanding the kind of scale of generation you would need to just generate hydrogen on the network, and what kind of storage you might need to soak up the supply demand mismatch. There was Project Cavendish, looking sort of similarly at a regional part of the country, but focusing more on London and the southeast, understanding how you might use the Isle of Grain and the facilities there to flow hydrogen into London, and how you might stimulate a demand through the industrial customers within London. There was the Hydrogen Flow Loop project, and that was looking at whether our existing X52 pipe can carry hydrogen at 30% blend, and how that performs compared to a new pipeline construction technology called MASIP. And then finally, this NTS Hydrogen Injection Project, and that was looking at if we were to go ahead and do a trial and inject hydrogen into the live network, what might that look like? Who would be the best customer to take at for a first stab? And then that ultimately led to the creation of the Future Grid project, which Tom is going to talk about now.
So the NIA for Future Grid is part of a wider programme of work. Future Grid is an ambitious programme to build an offline test facility using high pressure gas pipes to actually demonstrate that our NTS can take hydrogen. So the work that we've done to date to understand some of the issues is actually going to be demonstrated through this project. And a key step to achieving the Future Grid Phase 1 project is actually our NIA project Roadmap to Future Grid. So this project is key to developing the principles and the specification of the proposed offline test facility. It's building on the learning from our NIA projects we've discussed to date, but also taking in the learning from the other gas distribution networks on a range of projects, including H21, H100, High Deploy, and so on. So the key deliverables for this NIA is to help to actually input the key information for designing the test facility, allow us to develop a comprehensive master testing plan that ensures we cover off all of those issues that were identified, and actually can demonstrate that the assets can take hydrogen at a variety of blends up to 100%, and actually to also do some initial asset integrity testing and interpretation. So that allows us to feed in some initial results into that design of the test facility and also the master testing plan. So we're going to finish with a short video on Future Grid Phase 1 to give you a bit more information about what that project is and what it hopes to deliver. So at that point, I'd like to pass you over to the video and thank you from myself, Tony and Lloyd for listening to us today. Thank you.
Future Grid is an ambitious programme which seeks to build a hydrogen test facility at DNV GL Spadeadam. This will allow for comprehensive testing to demonstrate the ability to transport hydrogen within the National Transmission System, NTS. So, what does the programme look like? In Phase 1, we will build an offline test facility to demonstrate that hydrogen and hydrogen blends can be transported effectively, flexibly and safely in the existing network. In Phase 2, we will explore different deblending technologies to separate hydrogen from natural gas and demonstrate the impact of hydrogen on compressors. In Phase 3, we will open the facility to third parties for them to test their own technologies and run specific impact assessments. The test rig will be made up of a representative set of decommissioned assets, which can be tested at different levels of hydrogen up to 100%. So, what will the project deliver? A representative hydrogen transmission test facility built out of decommissioned assets to accelerate our move to zero carbon. Demonstration of the ability to operate the network with up to 100% hydrogen. improved collaboration across the industry, internationally and with other sectors towards their decarbonisation goals. World-class training facility to upskill engineers in constructing, operating and maintaining transmission assets in hydrogen. So, who are we working with? DNV-GL are our main delivery partner, building the facility and carrying out the testing, supported with technical assurance from the HSE Science Division. We are partnering with Northern Gas Networks to link with the H21 Project, which is building a distribution test facility at DNV-GL site. Fluxys are our equivalent in Belgium and are contributing a substantial level of hydrogen research to ensure a collaborative approach internationally. Durham University and the University of Edinburgh are academic partners who will ensure learning from FutureGrid and hydrogen prepares our future UK talent for the Net Zero Challenge. Phase 1 is an exciting new step in the transition to hydrogen and a net zero future.
LTS stands for Local Transmission System. The LTS Futures Programme is designed to develop the safety, technical and practical evidence to support the use of hydrogen in the LTS. The research work proposed underpins many aspects of the decarbonised pathway. The work will provide evidence informing network safety in order to determine the suitability of LTS network assets for hydrogen, provide the technical input to ensure decarbonisation of industrial clusters can be delivered, and it will define the role of the LTS in system transformation and the impact of hydrogen rollout and green recovery. To meet the projected hydrogen demand, new pipelines and repurposing the current network is required. LTS programme will complete work to decarbonise the LTS network. This will include providing the safety and technical evidence to install new LTS hydrogen pipelines, a live hydrogen trial of a repurposed LTS pipeline, which we have earmarked on an SGN network as the Granton to Grangemouth pipeline, deliver a blueprint to repurpose an LTS pipeline for hydrogen, and ensure all gaps are filled to repurpose the current LTS network for hydrogen. Current projects which will benefit from the future of the LTS or the LTS Futures Programme are the SGN projects as H100 Fife, East Coast Scotland's Industrial Cluster, Aberdeen Vision, Southampton Water Decarbonising Study, Project Cavendish, Cadence Highnet, National Grid's High NTS and H21. The first phase of the Future of the LTS programme was a scientific feasibility study which looked at repurposing the LTS pipelines for hydrogen and CO2. It included both looking at the compatibility of materials and the risks posed to people by pipeline failure. An assessment has shown that a significant percentage of the SGN's LTS pipeline consists of relatively low strength pipeline grades that operate at low stresses. Case studies were used to test pipeline risk assessment methods and to bridge any gaps in existing knowledge. These case studies included the mothballed pipeline from Granton to Grangemouth, which has been identified as having potential to be repurposed for hydrogen transportation. SGN held a workshop to share the findings of the work to date and to identify any new gaps. The workshop was held in Edinburgh in February, where both SGN and National Grid presented on the work that they had completed to date. In the afternoon, a workshop was completed with all of the attendees to identify gaps and a roadmap to go forward. It was agreed that a collaborative group with all the GDNs and National Grid and industry bodies should be formed to work to close these gaps. An SGN chaired iGEM group called LTS Futures has been set up. This comprises of memberships from all of the gas distribution networks, HSE, BEIS and other industry bodies. The group will work collaboratively to close any knowledge gaps outlined from the workshop and others identified through trials. The second phase of the work, High Technical, has begun. High Technical has 3 work streams within it. The first work stream is desktop exercises to understand the impact hydrogen has on inspection, maintenance and repair, repurposing pressure reduction installations, and building proximity distance and separation distances to parallel pipelines. The second work package is the development of hydrogen supplements to gas industry standards. So this is for TD1, TD3, TD4 and TD13. And work package 3 is updating the SR25 hazardous area standard for hydrogen. The work is with all of the GDNs and also with IGEM as the supplier who is overlooking all the work. High Technical will develop approved industry standards allowing requirements to be formalised and secure safe best practice. This is needed to ensure consistency in repurposing existing natural gas networks, construction of new assets, and to ensure compliance with legislation. The GB gas industry are driving forward towards live consumer trials in the near future. As such, it is important that the GB industry develop a suite of standards that deliver consistency and confidence in engineering practices deployed for such trial activity and further expansion of hydrogen for heat. The desktop studies within High Technical will close the gaps identified in the first phase of the LTS Futures for inspection, maintenance and repair, pressure reductions and a quantified risk assessment gaps. The results of the desktop studies provide the evidence-based research that will be fed into the TD supplements. The TD supplements will allow new hydrogen pipelines to be installed, allowing industrial clusters to be decarbonised, and provide requalification process which will include material testing for repurposing pipelines. The SGN LTS network was designed and constructed to operate with natural gas. However, the majority of the LTS network is no higher than X52 grade carbon steel and operates at below 30% SMYS, specified minimum yield strength, and therefore is theoretically suitable for hydrogen. The GB's LTS network dates back from the 1960s, and over the years pipelines have been manufactured to varying quality standards. Therefore, existing assets of appropriate grades of carbon steel, i.e. X52, may not be manufactured and welded to the same quality as equivalent pipe today. To understand if these pipelines can be repurposed for hydrogen transportation, material testing and further analysis is required. In order to develop a blueprint for repurposing LTS pipelines, it is proposed that a trial and demonstration incorporating SGN's Granson to Grangemouth LTS pipeline is undertaken. The mothball pipeline, currently filled with nitrogen, is deemed to be as being representative of the GB LTS network. Its spiral seamless pipe, X52 carbon steel fabricated in the 1970s. Repurposing live pipelines would be expensive due to the additional diversion work required to maintain security of supply. Material testing of existing pipelines of this vintage is necessary to understand how they will behave when distributing hydrogen. To support this work, SGN has secured a 1970s seamless X52 pipe from a recent diversion project. This pipeline sample is similar material to the Granton to Grangemouth pipeline and will be sent to Strathclyde University for lab testing. The testing will demonstrate qualification for hydrogen service. So this will give us a set of tests to qualify for hydrogen and will help with a design tool for material selection. It is known that hydrogen embrittlement, a hydrogen failure mechanism, is more susceptible to cold worked areas such as dense, weld, cold bends. Therefore, further testing is required on pre-strained areas. This will allow us to understand what defects we can accept in the pipeline, such as a 6% outer diameter dent, or without doing a repair. This will provide valuable input into P11. This work is proposed to commence very shortly and conclude in March 2021. The graphic shown encompasses the work that will be completed by High Technical, as well as the material testing completed in the labs. There are currently no methods for undertaking live repairs on hydrogen pipeline. The inspection, maintenance and repair desktop study under High Technical Project will review the repair techniques and their suitability on hydrogen pipelines. Further testing may be required on repair techniques and methods under a hydrogen environment, which can then be later validated at live trial. Following on from the pressure reduction installation and QRA desktop studies and SR25 update under High Technical, further work will be required to repurpose PRIs. The graphic shown shows the work anticipated. National Grid Gas Transmissions Project Future Grid will be investigating repurposing a decommissioned PRI. This work will fill in some of the gaps associated with repurposing PRIs. Under the PRI desktop study, the consultancy expert have issued out a spreadsheet to collate all the GDN's PRI asset data to fully understand which components require further testing. Work done under PRI and SR25 will allow GDNs to understand the effect of hazardous areas and understanding the impact of repurposing or rebuilding PRIs for Hydrogen Future. The LTS Futures programme is designed to develop a safety, technical and practical evidence to support the use of hydrogen in the LTS. In the graphic shown below, you can see the network safety and impact follows throughout all the aspects of the programme. To meet the projected hydrogen demand, new hydrogen pipelines and repurposing the current network is required. The LTS Futures programme will complete work to decarbonise the LTS network. This includes providing the safety and technical evidence to install new LTS hydrogen pipelines, shown here, going to an industrial cluster, a live hydrogen trial to repurpose the LTS pipeline on the Granton to Grangemouth, shown as the live trial blueprint for repurposing, delivering a blueprint to repurpose an LTS pipeline for hydrogen, and ensuring that all these gaps are filled to repurpose the current LTS network to ensure we can roll out and help to system transformation. To ensure the Granton to Grangemouth pipeline is suitable for repurposing for hydrogen, further material testing on the weakest part of the pipeline will be completed to determine the pipeline is fit for purpose to be repurposed for hydrogen. Once the material testing is complete, a repurposing study will be completed to ensure all gaps are filled for the live trial. The repurposing study will assess all known and new risks and assign frequency feeding into the detailed QRA in advance of the trial. One of the outcomes of the LTS Futures programme is an overarching QRA for the whole LTS network and individual risk assessments for each pipeline. The LTS Futures live trial will produce the blueprint methodology for repurposing pipelines, which will be informed by HAZOPs and hazards processed from the trial. The live trial will validate all the safety and technical testing completed in a controlled environment. The outcome from the live trial will feed back into the LTS QRA and also the Network Impact Safety Board QRA for repurposing the gas networks. Although it is anticipated that the pipeline Granton to Grangemouth will be representative of the GB LTS network, further testing will be required to ensure all relevant LTS assets are captured. This additional work will be carried out in collaboration with all the other GDNs. SGN have completed a review of the GDN's LTS pipeline data, and the majority of the pipelines, more than 90%, are very similar. The graphic below shows how the research-based evidence and the lab testing informs the QRA for the trial, and the live trial will provide the blueprint for repurposing, although further testing will be required. And those results and the live trial results will feed into the LTS and the Network Safety Impact Board QRAs. This will allow rollout for repurposing LTS networks to help to decarbonise industrial clusters and support system transformation. That's everything from me, but if you'd like to know anything else about the LTS Futures programme or anything to do with the LTS, please contact me. Thank you very much.
Hello to everybody watching. It's a pleasure to be able to present today at the Energy Networks Innovation Conference. My name is Sikandar Mahmood and I work for Cadent, who are the largest gas distribution network within the UK. I work in their Future of Gas team, primarily focusing on the innovation portfolio. So just to give you a brief overview of what I will be discussing today. So I'll touch on the strategy for decarbonising the UK gas supply and why we want to blend hydrogen into the networks. I'll then hone in on our project HyDeploy and the subsequent phases of HyDeploy which come under HyDeploy 2, and then give you an overall view of the wider picture in terms of Highnet, and I'll welcome any questions at the end. The majority of homes in the UK rely on natural gas for heating and cooking, and that's because it's well suited for the UK housing stock. The gas distribution networks have made some significant strides in working towards decarbonisation and reducing the carbon intensity of the gas network. Whether that's with the use of biomethane projects or innovation projects such as BioSNG, which looks at converting black bag waste into gas. And there's work going on across Europe looking at hydrogen blends and how they can work within distribution networks. And that's what I'll really focus on today. And it's all working towards progressively supplying closer to 100% hydrogen to selective consumers, such as heavy industry users, or using it for transport fuels in HGVs or buses or trains. Or can we use it for power generation and new developments? So what is the HyDeploy project? So HyDeploy aims to demonstrate that for the first time we can blend hydrogen up to 20% volume within the current natural gas infrastructure, and that can be done safely and efficiently. We're working with a project consortium which is led by Cadent. We're working with Northern Gas Networks, Keele University, who are the host site for the first demonstration, the Health and Safety Laboratory, who are focusing on that scientific evidence base, ITM Power, who provide us with the electrolyzer, and Progressive Energy, who are working on the overall project management. And there's real potential to deliver some carbon savings with HyDeploy. So why blend hydrogen into the gas networks? Well, there's a few reasons, and I'll touch on some of those. And one of the most important reasons is the fact that there'll be minimal disruption for consumers. We won't need to change the appliances that you have in your homes. So the boilers that you use to heat your homes, your cookers, your gas fires, we can keep those the same. We won't also need to change all the pipelines that we use to distribute the gas currently. And whilst we're making these changes to the gas composition, we can start to improve the hydrogen supply chain, helping us get closer to the goal of 100% hydrogen. And in the meantime, we'll be able to make some real carbon reductions. It's like removing 2.5 million cars off the road if we were to blend across the UK. And that's a real deliverable roadmap for deeper savings. The deployment of hydrogen as a low carbon energy vector is crucial to the UK in achieving the legislative targets of net zero by 2050. And hydrogen has been highlighted by numerous stakeholders, including the government's independent climate change advisors, the Committee of Climate Change, who outlined in their May 2019 net zero report that moving beyond an 80% target changes hydrogen from being an option to being an integral part of the strategy. So in terms of the timeline of the HyDeploy project, we started off in 2017 building the safety case for what would be our first demonstration project at Keele University. We built the safety case and then went on to install the equipment on site, and we're currently in the live demonstration phase at Keele. That's been extended due to COVID-19, and I'll touch on that in a later slide. After the Keele demonstration, we then aim to have a demonstration in the northeast of England. We are currently building the safety case for that and creating the design and install for the equipment on site. And following the northeast demonstration, we will do a final demonstration in the northwest of England, where we will follow the same process and tackle those evidence gaps that we weren't able to address in the Kiel and in the northeast demonstration. Conducting our first demonstration project at Kiel University was a real no-brainer. It's like a small town on gas. There's around 100 residential properties, some multi-residential buildings and some commercial buildings such as office blocks and laboratories. And because Kiel own and operate their own private network, it really reduced the complexities in terms of commercial arrangements. I touched on the safety case in one of my previous slides, but what does that actually mean? The UK has a strict regime in terms of safety. There's gas safety management regulations which stipulate that you can only have 0.1% hydrogen within the gas networks. So we were required to build on that safety case and create the evidence base to obtain an exemption to those regulations. So we carried out some work on appliances, testing the appliances to ensure that they operate safely on blended gas, looking at boilers, cookers, gas fires. We also carried out some testing on materials, the materials that consist in the pipelines that we have in our networks, such as plastic and steel and metallic pipelines. We also did some work on gas characteristics, so understanding how gas accumulates in somebody's property, understanding the consequences if blended gas was to ignite in comparison to natural gas. Also working on the operational procedures and the gas detection that we use as part of the GDN process. And finally, focusing on customer perception. Kiel University provided us our first opportunity to have hydrogen in homes and really understand the customer perspective. And grouping all those together, we were able to build a safety case and achieve the first exemption in the UK for that GSMR regulation, allowing us to blend up to 20% into the Kiel network. So this slide just shows us some of the pictures whilst we were carrying out the installation. It includes some of the testing that we did before we got on site at Kiel University, and then some pictures to show the equipment being installed on site. So what we're really looking at here is, I know it just looks like a lot of green boxes, but this is essentially the unit that blends the hydrogen, the units that produce the hydrogen, and in the bottom left picture you can see inside the unit which blends the hydrogen, the grid entry unit, and the picture in the middle on the bottom row shows us the gas composition quality measurements that we are doing. So you can see the gas chromatograph and a picture of one of the rhinology sampling boxes which we have strategically located on the Kiel network to ensure that we have the right odorant level when we're injecting the hydrogen. So this slide will help you understand how the process operates, and I'll try and simplify it. So the natural gas comes in on medium pressure, where you can see labelled natural gas inlet. That then goes into the hydrogen grid entry unit. We're producing hydrogen on site via the electrolyzer using a process called electrolysis, which uses electricity to split water into hydrogen and oxygen. The hydrogen is then stored in the buffer tank. The buffer tank then provides the hydrogen to the hydrogen grid entry unit, where it's blended with the natural gas. That blended mixture then goes around a volume loop to ensure that it's the correct composition of hydrogen and natural gas. That mixture then is released into the blended gas outlet in a medium pressure pipe which goes into the local pressure reduction station, where it's reduced in pressure and allowed to be distributed into the low pressure network at Kiel University. And it's as simple as that. So where are we now in terms of the HyDeploy project itself? I mentioned that we were able to achieve the exemption to the safety case. I mentioned that we completed the installation on site, which you can see in this picture here. That's the fully constructed compound. I then mentioned that we started the live demonstration at Kiel University, and we have been blending on site. We've not experienced any issues with the appliances in people's properties. We've not experienced any issues operationally in terms of the way we operate the gas network. And in parallel to the work that we're doing in the demonstration, we're also running a boiler project where we have 8 boilers, 4 running on natural gas and 4 running on blended gas. And what we'll do is at the end of the project, we'll strip down those boilers and send them back to the manufacturers, Firstly, to see if they can understand which one was on blended gas, which one was on natural gas without telling them. And then they'll be able to do some testing and understand if blended gas did have an impact to the components within the boilers. So moving forward from HyDeploy at Keele University, we step into HyDeploy 2, which is essentially two public demonstration projects, one in the northeast and one in the northwest. And the objective is to build on the work that we're doing at Keele University and demonstrate that blending hydrogen and natural gas can be done safely and efficiently in the UK distribution networks. And the outcome would be that a supplier is able to apply and inject hydrogen into the gas network just as biomethane producers can today. And we're using the same project consortium to really dip into that expertise and the experience that we have from Keele University. So looking into the trial principle across these demonstration projects, we want to start to reduce the additional mitigations that we're putting in place as that technical evidence increases. And that will help us build a picture for rollout of blended gas across the UK. Now at Keele University, we started off by doing gas safety checks on all properties. And we also conducted testing with bottled mixtures of hydrogen blends in the appliances. In the first public demonstration, we also want to test as many properties as we can using the gas safe checks. But we're starting to wean away from the bottle testing and not doing any bottle testing in the properties because we've been able to gather that evidence at Keele University. In the second public demonstration, we want to start to limit the amount of gas safety checks and again have no bottle testing, because to have a position for rollout across the UK, it's not feasible to be able to go into each property and continue the gas safety checks and continue the bottle testing. But we now have the technical evidence to enable us to justify that position and show that it will be just as safe as having natural gas in your homes. So the first public trial in the northeast of England will be located in a village called Winlayton, which is in Gateshead. And we'll be delivering a blended gas mixture to around 670 properties in that area. And we'll be building on the evidence that we've gathered at Keele University and really tackling those evidence gaps. So there's more properties here, there's a diverse user base, and it's on a public gas distribution network. So I want to finish off by showing you our vision for the Northwest. So the picture that you can see here is a programme of works which goes under the name of Highnet. And this really focuses on a central production area for hydrogen. It also incorporates carbon capture and storage. So the carbon is captured and transported using the orange pipeline that you can see on this picture. It's then stored out at sea. The hydrogen is then distributed using the black pipelines to heavy industry users. And this is really where HyDeploy comes into play. The evidence that we'll be able to gather using the HyDeploy project will allow us to tap into that source of hydrogen and create a blend of hydrogen for a wide variety of users within the Northwest, edging us that bit closer to the target of net zero. Thank you for watching my presentation on HyDeploy. I'm happy to answer any questions going forward, and if you're not able to get an answer for those now, feel free to drop me an email using my email address on this current slide. Thank you.
Thanks so much to our speakers and to all of you for participating in the Energy System Transition Building the Safety Case session. If you'd like to continue the discussion, you can visit our company's stands in the Innovation and Exhibition Halls, where you can access additional innovation project videos from the networks, chat live with project leaders and with technical experts. Also, keep an eye out for pop-up windows at the bottom of your screen that will take you through to our 3 p.m. group chats. One of these will be following directly on from this session's topic, looking at the hydrogen transition, how we're building confidence in the safety case. And this will be led by Nancy Thompson and Stephen Tomlinson of SGN. So that's all from me. I look forward to seeing you again in this room at 3:30, where we'll be discussing facilitating the energy system transition.